Right, our next example is about the problem of partitioning the complete graphs into complete bipartite graphs. So let me give you an example. So complete graphs are graphs where every pair of vertices are adjacent. So this is an example of complete graphs on 5 vertices, which we write by K5. Now, how can I partition the edge set? All right. Partition the edges of Kn into the edges of the complete bipartite graphs. How can I do it? So for instance, I can have, for instance, this is complete bipartite graph, K22. Right. And then I have a let's say K14. And then right, so K22 and then K14 and 1, K11 or K2. Let's say K2. No, K11. Yeah, that's K14 and then another K11. So I'm using 4 of them. Right? So I use 4 complete bipartite graphs to decompose K5 into decompose K5. Now, here's an interesting theorem, and this is best possible. This is due to Ron-Graham and Pollack in 1971. They proved the following: the edge set EKN of the complete graph cannot be partitioned into less than m-1 copies of the edge sets of complete bipartite graphs. Yeah, why is n-1 tight? I showed you one weird way, but there's an easier way, right? I take one vertex, look at all n-1 edges coming out, so K1 n-1, and remove it. What's left is complete graph on n-1 vertices, and I do it again and again and again, right? So instead of taking this non-trivial way, I could have taken the easier way, right? So K14 and K13, K12, and K11. So that's another way, and that's simpler way. So with m-1, you can always do it. The point of this theorem is that you cannot do it with less than m-1 copies of complete bipartite graphs. And I will show you the very nice proof discovered only in 1982. So suppose that the edges of complete bipartite graphs can be partitioned into T edge sets of complete bipartite graphs on AI and BI. Let's say, so AI, BI are subsets of 1 up to n, right? So AI So the AI, BI is disjoint, right? So AI is here, BI is here, and you are looking at this set of edges between AI and BI. Now, what I do here is to consider a polynomial. So let S of x so x is actually a variable consisting of n variables, okay? And I'm going to define S of x to be the sum of all product of xi and xj, right? Why not? So that's a polynomial. So for every edge, you have one monomial, right? Xi, xj. Because we can partition it into complete bipartite graphs, I can write it as a sum of all these things. For people in AI, I make a product of xj, and for people in K, for people in BI, I make a sum of xk. And I'm gonna sum over this from 1 up to t. And these things are equal. Why? If you look at the right hand side, if you apply the distribution law, it's gonna be the sum of the product between people in AI and people in BI. But every edge appears exactly once in some complete bipartite graphs, so each edge is counted exactly once. So when you expand it, you're going to have a sum of the product. So these two are equal. Right. So why is this useful? How can I use it? Well, let's look at this term, sum of xi squared. Well, each algebra will show that this is equal to that, right? Now, what's going to happen? Right. Now, let's consider the following equations. Sum of xj is 0 for j in AI. For all I in 1 up to t. Okay, that's one equation. I mean t linear equations. And sum of xi is 0 from 1 up to n. So these are t plus 1 linear homogeneous equations. And now note that t plus 1 is less than or equal to n. No, t plus 1 is strictly less than n, right? So what does that mean? So I have a small number of the homogeneous linear equations, so there must be some non-zero solutions. A non-zero solution x satisfying all of star. So why do I care about that? If you have a solution satisfying all of star, that means sum of xi is 0, so this is 0, and this part is 0, so that means s of x is going to be 0. So sum of xi squared is 0 and s of x is 0, so sum of xi squared is 0. So this means that xi is 0 for all I. Wait, that's wrong because we chose x to be a non-zero solution. That's contradiction. Again, we use linear algebra, right? Okay, so I should change my wording. Instead of using polynomial, actually what we are using is a linear algebra. We have a linear homogeneous equations, and whose number of them is less than the number of variables, so there must be a non-zero solution. All right, so that's a beautiful proof.